Okay, so hi, today we will talk about hardware-based security in Android. The agenda for today will cover 4 topics: trusted execution environment, verified boot, and root of trust, which is involved with this process. We'll take a look at the encryption mechanisms in Android, and lastly, shortly, we'll cover upcoming virtualization extensions to Android ecosystem. So let's start with the trusted execution environment, which is TE. Okay, so let's start with a few words about trusted execution environment. It is a dedicated, separate trusted execution environment, which is separate from the main operating system. Nowadays, basically all the devices running Android are running on ARM, so they often utilize this ARM trust zone, which is a hardware feature thanks to which we can create this hardware-backed isolated environment. It is used for execution of confidential operations. We'll talk a bit later about what are those specifically in this Android ecosystem. In this Android security model, the main operating system, the Android, is considered untrusted, so the critical operations involving some key operations, signing, encrypting, and so on, those are handled by this trusted execution environment. The trusted execution environment itself also, maybe you can say that it is provided by the trusted operating system, which is a small operating system provided by the hardware vendor typically. And on top of that operating system, we can run some trusted applications providing specific critical security services to the main operating system, which is in our case Android. So it is a pretty standard way, and Android heavily relies on this ARM feature. Then the next component we will talk about is Trusty. Trusty is like a specific implementation of a trusted execution environment. Google has noticed that many vendors provide some form of trusted execution environments and operating systems and trusted applications, but only in the form of binary blobs. So they went ahead and created like an open source implementation of a secure operating system. Currently, it mostly is running on Google Pixel devices. Goal is to provide some reliable and open alternative. Google say they would probably want other vendors to switch to that. They want to improve transparency and reduce fragmentation of the ecosystem, and also simplify development of trusted applications. But what might be worth noting here is that it's not global platform compliant. There is already existing standard for trusted execution environment, and ironically, most of the vendors follow that. So the Qualcomm, Samsung, and so on, they use their own proprietary trusted execution environment, but they are compliant, so it's actually possible to develop applications being portable using those APIs. But if you wanted to create application for Trusty, you need to follow Google APIs. So here we have a couple of examples of trusted applications we can use in Android. So as we said already, we use them for critical security areas, such as lock screen passcode verification. So whenever we provide a PIN or a fingerprint, so the biometrics or the face unlock with the camera. There are dedicated trusted services for each of those actions. And the matching of either the fingerprint or the camera image or the PIN or the passphrase is actually being made in that is isolated trusted application. And the main operating system merely receives a message that whether the authentication passed or failed. So that's how it looks like here. The other use case beyond authentication is key storage and key management, and basically all of the cryptographic operations. So the keys in the Android ecosystem are never exposed in a plain text form to the main OS, rather than that they are stored as blobs in the file system, and applications can use specific keys via specific trusted services, which provide crypto functions to the higher layers of the system. Another possibly interesting use case example is protected confirmation. Android has this trusted user interface for some high assurance transactions. We can create our application in a way that it would call a specific trusted application for this high assurance protected confirmation. Maybe not so interesting, there is also use case for DRM to manage DRM protected content. So that was the in general. Now let's take a look at Android verified boot. Before we go to the Android verified boot itself, we want to have a quick look on the boot process. This is a modern ARM64 boot process, and also specifically looking from the Android perspective. Depending on the hardware vendor, it may be a bit. The implementation might be a bit different, but the general flow should look basically the same. So we always start with some form of primary bootloader, which is typically stored in a boot ROM in a read-only memory, which are fused directly into the SoC. And it is our root of trust. Typically, root of trust is also connected to some public key, which is fused to the hardware as well. We will take a look at a few specific examples in a moment. So we have this first bootloader, which verifies using this fused public key, the second stage bootloader, secondary bootloader. And here we may have also like many proprietary bootloaders. We can have trusted firmware A provides also this component. The ecosystem here is very fragmented. But the goal of this component is to set up a secure and non-secure world and define the memory isolation boundaries. So in the later stages, we have a clear separation, which memory is dedicated for the secure world and which memory is dedicated for the normal world. So this secondary bootloader also loads further bootloaders. We have a secure payload, which is trusted execution environment OS, so it can be trusty, as an example from the previous slide, or it can be some, for instance, Qualcomm or Samsung specific operating systems. And finally, we also have so-called non-secure firmware, which is some form of bootloader booting Android finally. So it can be U-boot, Linux, CDK2. It's also not standardized area yet in Android. We already mentioned root of trust, hardware root of trust. We want to talk about verified boot, but for the verified boot to be really functional, we have to start somewhere, and we need to root our trust in some immutable part of the system. Android defines some of the requirements that hardware vendors must follow in order to be compatible with this verified boot feature. And one important one could be the C1.3, which says that the device must start verification from an immutable hardware key that is a root of trust and go all the way up to the system partition. There are more requirements like that, and there are, as you can see, there are not very specific. There are some. This compatibility program covers like a lot of area of the Android compatibility. This integrity part is not the most important one, but it's the most interesting for us. There are also a lot of tests for the Android functionality to see if your device can be compatible with Android, but they mostly focus on like higher level features than what we are interested in here. So what we have is those text form requirements only. So maybe let's take a look at some examples how hardware vendors interpret that and implement that in practice. Some vendors publish some of the documentation in terms of the secure boot, verified boot. They call it their own way, differently. But essentially, the idea is generally the same, that we have a boot ROM, that we have some fuse, which is inside SoC, that during the manufacturing we fuse the public key, and that is our root of trust for the next stages. So we have those vendor-specific bootloaders, vendor-specific trusted execution environment. So it's very fragmented in this area, and then we jump to the Android kernel using this Android verified boot feature. We will cover a bit more in a moment. Another example is Qualcomm. They also have this primary bootloader in boot ROM. Then it loads it creates like secure world, non-secure world, and XBL sec acts as root of trust for the trust zone images, and the XBL bootloader as root of trust for non-trust zone images and verifies them later on. And we can also see in some documents from Qualcomm, we can read that we have similar mechanisms, that we have some form of fuses or maybe even hard-coded the key in hardware ROM code. Another example is Google Pixel. Here it's a bit different, as we have a separate security chip, which is Titan M. It's derived from the Google Titan chips originally produced for server boards, but we have also a version of Titan M, which is smaller and more targeted towards this mobile ecosystem. And in this case, this root of trust is provided by the external chip, which bootstraps the whole boot of the platform. So verified boot. So the Android verified boot now, what that is? Its main goal is to ensure that all executed comes from the trusted source, and by all code we mean the OS code. So we start verification from the Android kernel, then all of the partitions, and so on. because that's what the Android focuses on. The previous part is more specific to the vendors. The important part is to establish a full chain of trust, starting from the hardware protected root of trust. Each stage verifies the next one. What is also important, we will see in the next slides, that the verified boot focuses on communication of the state to the end user. Just mentioning ZDM Verity briefly, it's like a Linux feature, not a hardware feature, but it's used to verify the partitions, to verify the integrity of the partitions. We'll see in a moment that a verified boot flow also has like a error code for that failure. An interesting feature is user settable root of trust. On some devices like Google Pixel devices, you can change the key which is used to verify the Android OS to your custom one. So you can run a custom OS, not only the OS approved by the hardware vendor. In this case, it is Google. So this path is used by the custom ROMs, such as Graphene OS, during installation, where we unlock the bootloader, we set custom key and we lock the bootloader back. It is a bit similar to the secure boot, UEFI secure boot, a custom keys mechanism. So there are a couple of boot states that can be reported by verified boot. So let's take a quick look on the user experience. We have a yellow one, which means that the device is locked with a custom root of trust. It will always appear if we have a custom root of trust installed. For instance, if you have a Graphene OS on each boot, you can see this screen. It proceeds automatically after 10 seconds, so it doesn't block your boot. But you have a time to compare this hash, and you may go to OS vendor, or maybe if you build your own OS, you may compare this hash to make sure that you are running the OS you wanted to run. And then we have orange screen, which means bootloader is unlocked, which essentially means there is no verified boot protection. There is software integrity is not guaranteed by verified boot. I mentioned ZDM Verity just a moment ago. So if there is a problem with integrity of any of the partitions, we can see a red screen. And by default, in this state, the device powers off automatically. But there is option for the user to bypass it and boot regardless. I mentioned that the bootloader area is very fragmented. Google also working on making it a bit more unified. So they're introducing this generic bootloader, which is essentially a UEFI application written in Rust, of course. So we can guess that it will be a standard in a few versions. Since Android 16, it says it's strongly recommended for ARM64, so basically for all Android phones. And we may guess it may become mandatory in the future, so we may have UEFI on all Android devices in a few years, which is a requirement for hardware vendors. Let's take a quick look at encryption. All user data on Android is encrypted using symmetric encryption keys, and we don't use full disk encryption, we use file-based encryption. So whenever application tries to get data from disk, it's encrypted, decrypted before passing to the application, and before when the application wants to write data to the disk, it is automatically encrypted before committing to the disk. So all of the user data is encrypted all the time. So why this switch to the file-based encryption, because previously when the full disk encryption was used, it was a problem that when after we boot the device, some of the services are not working because the disk is encrypted. So now we can have a specific parts of the system being decrypted automatically even before user enters unlocks the phone. So for instance, services like alarm or crucial system services can be already operational even before we unlock the device. So as a result, we also have like two kinds of storage locations with this file-based encryption. We have device encrypted, which is encrypted automatically as soon as the device booted and passed the verified boot phases. And we also have credentials encrypted. So those files are only encrypted, decrypted when verified boot passes and also user unlocks the device. So that's recommended for most of the data, but if there is some specific service that need to be executed or access some data before screen is unlocked, there is an option to do that. So quick look at the hardware-backed key store. So as we already know, we have two ways of storing the encrypted files. So device encrypted and credentials encrypted. And of course, trusted applications are involved in this process. We have this gatekeeper trusted application, which provides authentication services to the Android, and we have this KeyMint trusted application, which is used for storing and managing keys. So keys never are exposed outside of the trusted execution environment. So we have like these two types of keys. So if you have the device encrypted key, then as soon as the verified boot passed, the KeyMint can release, not release keys, but can perform some decryption operations on specific files, and those files can already be available to some services that must be running even before the screen is unlocked. And for the others, we need this verified boot component to pass as well. But we also need a user to provide valid credentials, and only after both conditions are met, we can decrypt the credentials encrypted files, which are available only after user unlocks the device. And very shortly about the Android virtualization framework. We can say it also uses some hardware feature, which is a virtualization feature. It is quite a new approach in Android to provide an option for even more sandbox environments. So it consists of the PKVM hypervisor, which is a modified Linux KVM that we know. It provides MicroDroid, which is a minimal Android-based OS, which can be put inside of the protected virtual machine. And the goal is to provide a framework for developers to easily transition from regular applications to protected VMs. So that is why we have this Android API inside of this VM, so the traditional application can be quite easily transitioned into protected VM, which provides stronger separation mechanisms. So that would be it for today. Thank you.
Thanks, Maciej. Yeah, a lot of interesting stuff. Like, I guess, yeah, we are behind the schedule, but for me, of course, is the most interesting is this OTP fusing. You mentioned this is done on manufacturing floor, but that's kind of weird because in terms, of course, that's recommended, and of course, everyone should do that. but on the other side, you're buying chips from someone, like, and maybe producer of the phone is not the chip vendor. And what in that case? So someone needs a tooling for going through that process, yeah, I guess.
Yes, that's really not. Yes, obviously we know we use like those tooling ourselves, so we know how they look like roughly for some vendors. Yeah, but it's not something that Android cares about at all. They just say that we need root of trust, which is tied to the hardware, and then it can later be used for verified boot of the operating system. What is they care about mostly?
And so how they call the software? I don't know. Someone have to leverage this this whatever was fused, yeah. So there is like boot ROM, I guess, that leverage that always boot ROM expose that functionality.
No, boot ROM doesn't need to expose anything. We have to pick a chain of trust that each component verifies the next one. So we start with the boot ROM verifies the next bootloader, and the next bootloader may use some boot ROM feature, but may also use its own verification functions, and maybe even a different key, maybe even stored inside the binary. That's totally up to the developer. For this Qualcomm, they say, sure about the details, but they have original root of trust, which is baked in hardware, and then they have two paths. And normal XBL is verifying the next stage. So possibly we have maybe a different key somewhere here, also here. So this one is possibly the fused key is possibly used to verify only those two, and those two can use some mechanism also to verify the next stages.
Okay, yeah, obviously, like the code which to maintain the life cycle of fusing and so on, and like kind of talking with the fuses is the target of attack, because I guess like
it is, but it's like very fragmented, diverse, and it's not in this what Android cares. Maybe they care of their devices, of course, for their implementation, but for the vendors, yeah, there might be bugs here in this whole area on different stages of verification, and yeah, if there are, it's like a responsibility of a specific vendor.
That's interesting. That's interesting that there is that it doesn't sound like Google enforce any. Like I think it has to go in that direction, because it's like with Microsoft, yeah, Microsoft enforced on the OEMs certain security properties, and like seems that Google will go that path, or maybe will dominate the market.
We can say they do. They do specify this verified boot flow, because this verified boot flow must be implemented in this OS bootloader, which is also provided today by vendors. So vendors must follow some guidelines from Google, or maybe also they have also this library AVB. They can integrate to their own bootloaders to load the Android kernel. And
yeah, I just wondering like what are the evidence of that vendors providing software can just fake it, yeah, and or not do the good job. So what are the really verifiable evidence? Yeah,
there are some tests in this suite I showed, but as I said, not everything is scripted in tests. So yeah, I'm not sure.
Okay, sure. Okay, like let's switch to Kamil, and thank you very much, Maciej. That was very interesting.